All right, calculus, we're continuing just for a short bit with the cross product today. You probably need practice working with it as much as anything. But for the cross product, we get a vector such that the cross product is perpendicular to each of those two vectors. So we've got a solution in 3 space. That allows us to use the dot product to check our answer. So the dot product can be a test. Whoops. So you would check that V dot U cross V equals 0 to check that it is perpendicular to each of U and to V. So our dot product is a check. It has a magnitude. The magnitude of the cross product is the magnitude of U times the magnitude of U sine the angle between them. And the direction is found from a right-hand rule. We had the formula yesterday, which we'll put back up for you, and we will also use the down products, down products, up products. I should be down first. Okay. Here are some properties of the cross product. So A cross B is equal to negative B cross A. And so this is going to get tricky with my hands. But I'm going to have this one as vector A. Let's say that the magnitude of vector A is 10. And we have vector B. And let's say that vector B has magnitude 8, because they look pretty similar. And there are 40 degrees between them. I can find the magnitude of that, but the direction could be different depending on the order. So the magnitude of A cross B I could find quite easily. Would be 10 times 8 sine 40 degrees. Okay. Let's check what direction A cross B would be. So my forefinger goes along A with my right hand. My middle finger follows B. And I have, as I am pointing along those two directions, my thumb is going into the blackboard. I just cannot spell. I'm sorry. Into the board. Okay, let's check that that would be the same for negative B cross A. So negative B is a vector that goes in the opposite direction of B. So it would have the same magnitude of 8. A would still have a magnitude of 10. The angle between them. Okay, so if I had negative B cross A, I would have the opposite of B. I cannot fit it nicely onto this diagram. I'm trying. Negative B goes this way. And we know the cross product is tail to tail. See, I still can't draw it in the right. Okay, last best attempt. Negative B cross A. I'm saying that those two things are equivalent. The magnitude of negative B cross A would be the same because I would have 10 and 8, and I would have sine 140. Sine of 40 and sine of 140 are the same. So the magnitude of negative B cross A would be the same as, so I'd have 8 times 10 sine 140. So the magnitude's the same, but is the direction the same? So if I have negative B first, that's where my pointer finger goes. So my pointer finger goes along negative B. My middle finger is going along A. When I do that with my right hand, my thumb is pointing into the blackboard. It is the same. So the conclusion to the matter is that this premise is true. That means that the cross product is not commutative. You cannot just cross product things in reverse order. It is different. Order matters. So A cross B is equal to negative B cross A, not commutative. Property number 2 is that the cross product is distributive. So we have the distributive property in two places, but notice that A cross B plus C does not give you the same result as B plus C cross A, because this is not the same as that. Order matters. So we have to be careful. The distributive property is true. Order matters. And we have scalar multiplication. Our last property of cross product is U cross V is 0 if and only if U and V are collinear. So part A, let's see if it goes in one direction. So if we know they're collinear, then the magnitude of U cross V would be magnitude of U, magnitude of V, sine 0 degrees between them, if they are collinear, and that will give us 0. If the other direction, if the cross product is 0, then the magnitude of that cross product is 0. Does that necessarily mean that they're collinear? Well, then I know that the magnitude of U times the magnitude of V sine theta is 0. And we said that these only work for two non-zero vectors, U and V. So I am saying that sine theta is 0. Well, that means that theta is 0 or 180 degrees. And so we would say that therefore they are collinear. Same or opposite direction. So this gives us a great test for collinearity, is when the cross product is 0. So number 1, we can use the cross product to test for collinearity. Number 2, let's use the cross product to have a look at this triangle. So if I have formed a triangle with vector CA, and CB, so these two vectors have formed a triangle, and I've got a vector from here to here. I am going to use common notation that we use in grade 10. So little vector C, I'm going to call that little vector C. And this little vector B, and this little vector A. Okay? So I know that little vector C, the way I've drawn my vectors, is equal to little vector A subtract little vector B. And I have my arrowhead going in the wrong direction. It should be down here. Sorry. So from my understanding of collinearity, I know that any vector cross itself, well, that will have 0 degrees between it and itself, would be the 0 vector. So from this particular diagram, I know that vector C cross with A subtract B, which is also C, would be the zero vector. Using properties of the cross product, I can say that C cross A subtract C cross B is the zero vector, which means that C cross A is equal to C subtract, sorry, that was C cross B, C cross B. By definition, vector C cross A is the magnitude of C, magnitude of A, sine the angle between them. So in this particular diagram, C and A have angle B between them. Okay. Cross product of C and B would be magnitude of C, magnitude of B, sine the angle between them, which would be A. I can divide both sides by magnitude of C. So magnitude of A sine B equals magnitude of B sine A, and we have just proven the sine law. Divide both sides by sine A, divide both sides by sine B. That's kind of cool. The third and fourth interesting thing from the cross product we're going to look at tomorrow, the moment of force. We're going to look at torque in bicycle pedals, area of a parallelogram. We're going to use a cross product for that. And lastly, I want to look just briefly today that we can test for coplanarity using the cross product. Let's have a look at vectors u, 2, negative 1, negative 2, v, 1, 1, 1, and w, 1, negative 5, negative 7. We're going to look at u dot v cross w, called the triple scalar product. Actually, you'll never be asked for that name, but I'll give it to you. All right. So I would like to find u dot this vector v cross w. So I'm going to find v cross w, and I'm going to use the up products, down products, or down products, up products. So v goes first, 1, 1, 1, 1, 1, 1. W is second, 1, negative 5, negative 7, 1, negative 5, negative 7. Just want to be able to go up a bit. Okay. So for my down products, up products, I get rid of the ends. Down products, up products. My down products would be negative 7. My up products would be negative 5. 1, negative 7. Negative 5 and 1. I subtract those. I would have negative 7 subtract negative 5 is negative 2. 1 subtract negative 7 is 8. Negative 5 subtract 1 is negative 6. So I want u dot with this cross product, negative 2, 8, negative 6. I just rewrote it because it's getting a little messy here. So I want the dot product between u and v cross w. And I am going to get 2 times negative 2 plus negative 1 times 8 plus negative 2 times negative 6. I get negative 4, negative 8, Positive 12, I get 0. So my premise to you is that U, V, and W are coplanar because I've had a 0 from this triple scalar product. Why do I know that? Well, what I know is that U is perpendicular to whatever whatever V and W are perpendicular to. Okay, let's try that again. U is perpendicular to what V and W are perpendicular to. The cross product of V and W gives something that's perpendicular to both V and W. U is perpendicular to that, so they must all be on the same plane. This gives us a good test for coplanarity. If U cross U dot V cross W is 0, they're coplanar. If they're not 0, they're not coplanar. Okay, we're going to get you to just play with the cross product a little further today. We'll do some applications tomorrow. Page 408, 8, and 11. And it wouldn't hurt for you, if you get it done quickly, to look ahead to tomorrow's stuff. Tomorrow is the applications of both the dot product and the cross product, and that might take a little bit more work.